We've seen a variety of different stochastic models that can be used to incorporate randomness into our description of a dynamical system. We looked at modeling rental cars by flipping coins to determine the final destination for vehicles. We looked at our epidemic model, where again we thought about coin flips as determining whether a person should get sick or get better. And then we also looked at some random walk models, which allowed us to incorporate spatial information about how people move. And you can combine those models to create even more interesting models that have both space and random sorts of events. Now, most of these models have been sort of I would say consider them a sampler of sorts of some of the things that you can do with stochastic models, but we haven't really dug in very deep and tried to actually build a model from scratch and use it to answer some interesting questions. So in this video, we're going to look at a question that is very pertinent to pretty much anyone, and that is, how do you save for retirement, and how can we use models to help us do that more effectively? So the scenario we're going to look at is suppose that upon graduating from Hillsdale at the ripe old age of 22, you've decided that you would like to start setting aside money so that you can retire in 45 years at age 67, and you'd like to be able to survive that retirement comfortably. And what that means is you would like to have a guaranteed annual income of $50,000 until you die. All right, and I'm just picking an arbitrary number. Each person may have different expectations or different expenses depending on where they live and their lifestyle. But as a baseline, we'll use $50,000 per year. And the question is, how much should we save each month to reach that goal? And so we're going to explore this question from a variety of different angles. We're going to look at it using some of our deterministic dynamical systems model, and we'll also look at stochastic models. All right, so we're going to start off with some assumptions. The first assumption we're going to make is that we're going to need to have $2.5 million by age 27 to retire comfortably and securely. Now, that is a non-trivial assumption. That would certainly require some justification. You'd have to look at, based on your nest egg that you've accumulated at that age, what sort of returns do you think you would get? How long do you expect to live so that you're not going to run out of money? And so there's a whole lot that would go into that, but we're going to focus primarily on the saving part rather than the spending once you retire part. And so we'll just use that $2.5 million as a baseline. And by the way, that's not an unreasonable amount. In fact, that may even be low, depending on the types of investments that you use in retirement. You may need even more than that for something like this. All right, and the second assumption we're going to make is that we are very, very stoic. We're able to handle the ups and downs of the market. We're able to deal with risk without getting too stressed out. And so we're going to invest aggressively in the stock market when we are trying to save. And then once we retire, we can switch into some sort of more conservative investment. Okay, now these are, again, simplifying assumptions just for the purpose of illustration. I'm not saying this is actually how you should invest your hard-earned savings. All right, so if we want to actually be able to predict how much we need to know how the stock market behaves. And so the first thing you might do is go out and find some data about how the values of stocks in aggregations of stocks like the S&P 500 index behave over time. And if you were to go back to 1950 and you account for the growth of the stock market with dividends reinvested, and you account for inflation using the consumer price index, that you would see that a dollar invested in 1950 is worth somewhere in the ballpark, well, at least in 2016 when I created this graph, it was worth somewhere around $40. That went up pretty significantly over the last couple of years, and then in just the last couple of months, we've basically walked back a lot of that growth due to the coronavirus outbreak and other circumstances. But if you were to look at just the average rate of return, if you were to just fit some sort of exponential model to that data, what you'd see is that you either could describe this with around 0.4% interest per month, or you could think of that as 5% interest annually. And so you could write down a nice little model where the value of that $1 is 1.05 times raised to the t over 12, where t is the time in months. So after 1 month, you'd have 1.05 to the 1/12, which is around 1.004 times what you started with, and that just grows from there. Okay, so that would be deterministic model, that's a data-driven model, right? And you could determine the appropriateness of exponential growth using our logarithmic transforms that we discussed earlier, but it seems like it fits the general trend. Now, of course, it misses some things, given that there was a really, really fast period of growth right before the year 2000, followed by recessions that led to actually decline in the value of the S&P 500 over the next 10 years or so, and then another rapid period of growth since then. So we're missing all of those ups and downs of the markets, but on average, this does give us the right behavior. Okay, so with that in mind, we can expect that we're going to have about 5% returns each year, or 0.004% returns each month, 0.4% return. We could then write down a model for this, where we use a difference equation to describe this. And so if we start with an initial retirement savings of 0, and we make payments of amount B each month, and we get 0.004, so a 0.4% return each month, then the new value of our investment after a month would be 1 plus 0.004, so the old value of the investment plus 0.4% of the amount we had before, plus our payment amount. All right, so this is nothing new here, very similar to models we've looked at thus far. And the nice thing about this difference equation is that it is a linear model, and so we can actually say a whole lot about how it's going to behave over time. All right, so if you were to go to your textbook or back into your notes, we'll notice that we wrote down a nice analytical solution. Now, quick caveat, the way that we wrote down this analytical solution was assuming that the equation was an plus 1 equals r times an plus b. And in this model, we have 1 plus r instead of r. And so this formula is going to look slightly different, but it is going to be just a quick modification of that analytical solution. And the analytical solution in this context would therefore be, you're going to take some constant, multiply it by 1 plus r raised to the n, where the n is the number of months since you started, and then subtract b over r, where again r is the interest rate. And that equation should give us the correct answer for our initial condition. So if we plug in n equals 0, we'll get a0 equals c minus b over r. And so c must therefore be equal to a0 plus b over r. And so this parameter c, we can find its value once we know the payment amount that we're making and we know the initial investment. And once we've got that, we can start to compute the value of the investment at future points in time. Okay. Now, if you recall, our goal was to have $2.5 million saved after 45 years. So after 12 times 45 months, which is 540, we want the value of this to be 2.5 million. And so we could use our analytical solution to find exactly what type of monthly payments would be required to achieve that goal. And that amounts to just setting a 540 equal to 2.5 million. And then using our formula for 1 plus r, which was 0.004, raised to the n, where we're interested in what happens after 540 months. So we'll put a 540 there, times a0, which was 0, plus b over r, minus b over r. And if you solve that equation for b, you end up with the solution $1,309.95. So if you were to save $1,300 a month and you were to get that 0.4% monthly return or a 5% annual return, then what you will find is that you will end up with, again, on average, $2.5 million at age 67. All right, so there you go. If you want to be a millionaire when you retire, that would be what you need to save. By the way, that is adjusted for inflation, so this is not actually going to be a raw dollar amount of $2.5 million, but rather that would be actually more, but that would be $2.5 million in today's dollars. Okay. All right, so if you actually generate a numerical solution to that model, this is what it looks like. And you'll notice that does not look a whole lot like returns on the stock market. Right? Returns on the stock market are not a nice smooth curve. They don't just grow exponentially, but rather there are a lot of fluctuations. There's ups and downs. The market rises and falls, and none of that has been captured by this model. And so this model, although useful for giving us a starting point, right? We now know how much we would have to save to, on average, have the right amount. It does not really give us a sense of our risk, because risk is significant here. You know, we don't have any guarantees that this is actually going to be the outcome. This is just the average outcome. So with that in mind, we might want to modify our model to incorporate randomness. We might want to introduce a stochastic model, and we could do that by introducing a variable rate of return. Instead of using r equals 0.004 consistently, we could generate random rates of return that are consistent with actual stock market returns. And then from that, we could see, well, what will it look like after 45 years of those random returns? And once we've got one simulation done, we can simulate this many, many, many times, and then look at things like what is the probability of meeting our goal for various different saving amounts. Okay? All right, so let's look at how we could do that. The first thing we're going to need to do if we wanted to simulate this process in a realistic way is we need to actually know what are the rates of return in the actual data. So there are a couple of ways you might go about this. One, you could actually draw a nice histogram of the percentage return for the S&P 500, the actual value of R. And you'll notice here on the left, so this is the actual data. That is, there were 798 months in the data set that I looked at. And the middle of that distribution looks like it's somewhere close to zero, which means on average, we don't make a ton each month. But if you notice, it's actually slightly above zero. So a typical month, you do gain just a little bit. However, there's a very wide spread here. We have some months where the gains were quite positive. 0.1, that's like a 10% gain in a single month. On the other hand, there's some months where it was really, really bad. Negative 0.2 over here, that was a really bad month. I think that was probably during the 2008-2009 financial crisis, where the S&P 500 dropped 20% in a single month. So that's really awful. And so there is some chance that you could do really, really well in a given month, some chance that you could do really poorly. We need to somehow be able to incorporate that into our model. And so there are two ways that you could do that. One is you could try to approximate that distribution with a normal distribution. And it means fitting a bell curve to the data. And you can do that very easily. The way to fit a bell curve to data is you just calculate the average and you calculate the standard deviation of the data that you have. In this case, if you compute the mean, you can use a command called mean, appropriately named in Octave, and you'll find that the average return, according to this way of calculating, is 0.0054, and the standard deviation is 0.0349, and that means that we could use something like rand n times 0.0349 plus 0.0054 to simulate random rates of returns that fit that distribution. Right? So that's one way we could do this. Another way that you could do this is that you could actually take that list of returns, think of that as just a list of random numbers, and then you could randomly draw from that list. And one of the reasons that might be a better approach is that it looks like when you compare the data to our normal distribution, although they look similar, they're not exactly the same, right? This is actually on the right is data drawn using a command like rand(n) times this decimal plus this other one. And you'll see that, yes, the center looks like it's in the right spot, and it does have roughly the correct shape, but the probability of getting really, really high or really, really low returns doesn't necessarily match up here. So although a normal distribution wouldn't be a terrible model, you're probably going to underestimate the risk of having something really, really bad happen if you use this model. And so the other way you could do it is imagine X, or let's call it R, is our returns. You could generate a random number from 1 to the length of R, which would be a random number, a random location within this vector. And so let's call that I. And then if you just picked out R of I, that would remove the rate of return that corresponds to that randomly chosen location. And you could then apply that for the next month and then repeat the process again. And so that would allow for these sorts of extreme events where the market really drops dramatically to happen once in a while, but it would do so very, very rarely because they only happen very rarely in the data that you have.